working, but the smartboard appears to be working. And watch it like die in the next 40 minutes. Okay, so strain gauges, boot. So strain. So there are a couple of different ways to measure strain in a test specimen or some object that's undergoing an operation or whatever. And you might think that, okay, this is kind of dumb, right? We can just like measure we can compute the stresses on it. But the trick is, like when we went through a Saint Venant's theorem way back when, we could kind of say, okay, if I have, say, like a bar in tension, the stress, it's called the stress in kind of like the middle of this bar will be nice, uniform. It fits all the assumptions that we've been making, right? And then we said stress around any applied load is going to vary dramatically from that, and in some strange way that is difficult to compute. And that's where we start getting into the world of like finite element models and computer simulations of materials. It's very difficult to a hand computation and get the stress distribution near a load. You can do it after it's kind of settled out to some average value, but it's difficult to do it near some applied load. And we also said with this that this is for a bar of uniform cross-section. If we start to vary that at all, we get all kinds of crazy stress distributions and concentrations. So for any kind of structure that would be of interest, say like a wind turbine blade or some part of a drilling string that has all kinds of irregularities along it, or a camshaft, or even like that cart, like a truss on that cart, it's not physically feasible to compute a stress distribution throughout the structure if you really want to get an idea of what's going on. And that's a big deal for things where your weakest point might not be at, say like we have our cantilever beam and we're pressing it down like that. We might intuitively think that the point that this thing is going to fail is where? At the wall here, because that's where the greatest bending moment is going to be. Because you have the force, greatest moment arm, greatest bending moment is going to happen here. It's probably going to fail there. But say that this is something like, if I'm looking down from the end, say that this is like a wing or something. So it has a very thin skin panel going the full way around. You can sometimes encounter something called panel buckling, wherein the skin, because it's so thin, will actually fail in compression before this whole thing will break in bending at maybe an order of magnitude less, so over 10 times less force, which is super intense. But because of how this force is being applied, because of how loads are being transmitted in a somewhat strange way, I mean, you have a really curved surface, you might have a whole ton of rivets along this thing. There's not really an intuitive way to figure out what the actual stress distributions are. So the easiest way to figure out what's going on is actually not to compute stress, and we can't really measure stress in a way. The easiest way now is to compute strain, or measure strain, really. And so there are a bunch of different ways of doing that. There's something called a Bragg diffraction grating, which has gained popularity recently, where you have what's called a piece of fiber optic cable, and it's taped down to the test specimen, and you look at how the wavelength of the light changes. But kind of the classic method is a strain gauge. So this guy is just a little piece of wire running, which called running back and forth inside of a film. You guys can pass this around if you want. And in the classic way of using these is you take your gauge. So that's like a side view of a gauge, and you glue it down to your test, and you glue it down to your test specimen, and the assumption is that the gauge will deform with whatever your test specimen is. So as that's what I was going to bring in. Oh well. So as this piece of metal, say, deforms longitudinally and laterally, the gauge is going to deform at the same rate. And what that does is it stretches the metal of the wires. And because if you go back to the definition of electrical resistance, that's what's called proportional to the length of whatever the resistance element is, in this case the wires. So resistance of this gauge is proportional to length. If you want to write it out, it's called proportional, like length over area times whatever the resistivity of the material is, but the point is that it's proportional to the length. So as the gauge stretches, the wire gets longer. So you have a change in resistance of the gauge itself. And you'll often call it, if you look at strain gauges, you'll see some sort of gauge factor quoted, which is, here it is. It's called, I hope this doesn't crash now. Which is the quotient of how the resistance of the gauge changes. There we go. So like the gauge factor is the change in how the resistance of the gauge changes in response to a change in strain. And so for a given amount of strain in the material, you get a change in resistance, at least over some range of applicability. And because strains are usually really, really, really low, like a couple of percent, if not less, right? This linear relationship holds decently well. And that's so if you have your material, you have your gauge sitting on it, and it's straining at the same rate as the material that it's glued to. You can use the gauge factor to correlate the resistance of the gauge that you can measure directly with how much strain is going on. And from that, if you know the characteristics of the material, you can find stress. Sound good? Sweet. So that's pretty much how strain gauges work. Yeah. Strain. So strain is defined as a change in length over an original length. But we're also talking about it kind of in the context of like a Hooke's law kind of thing, where it's related to stress and all that. That being a simplified version of Hooke's law. Remember the strain equations we had yesterday? That'd be the more full version of Hooke's law in like a 2D context. Okay, cool. All right, so how do we get there from here? So there are a bunch of different ways that people throw down strain gauges. One of them, so what I did here is just have one in the lateral direction, the circumferential direction, if you will, and then one in the longitudinal direction. You also see them like this, in a 45-degree strain rosette. The idea being that we can say that this is your block material. So this would be like the X direction. This would be like the Y direction. We have a gauge pointing in X and Y, so we can directly measure the strain in X and Y. And that 45 degree gauge, that guy here, that allows us to build a relationship for shear strain too. So it turns out, here we go, you can get shear, it's called, you could get shear strain from that guy. Like that, kind of the same way that, how do I want to say this? Kind of the same way that you can, how do I want to say this? The same way that there's a Poisson's effect kind of relationship between the elastic modulus and the shear modulus for an isotropic material, you can do the math with these to find the relationship between strain in some angle direction coupled with the lateral and longitudinal strains and get a relationship for shear strain like this. And if you wanted to generalize that more and say, well, what if I put my gauges in any given direction? You can, and would I be able to do some strain transformation and get like principal strains? And the answer is, why, yes, you can. And it's like that. So that's another her relationship. Don't worry, you won't see that on a test. The 45 degree I might throw down because it's really straightforward. And to be honest, you're not going to see arbitrary strain rosettes floating around. This is more or less just saying you can work strain transformation equations in order to get principal strains. And given strain, you can get stress working back, which called working back through your plane stress equations from last time. And there you can go to Moore's circle, you get a failure criteria. And this is, in a nutshell, materials testing. Like when they go to test up. Like I remember a presentation at a wind turbine blade conference. There's a group up in Boston, and they instrument a 40-meter long blade with hundreds of strain gauges just all over the frickin' thing. And they're essentially just working these equations to see where the thing fails, what loads it fails at, what stresses are present, all that kind of thing. Just understanding what's going on in the material. So this is kind of the path from beginning to end: obtaining strain from a specimen, parlaying it into stresses, building a Moore's circle, and seeing what's going on. Cool beans? I think it is anyhow. Okay, so that's strain gauges. Now for the fun part. Make sure I'm on a good program. Sweet. All right. So now for shear and bending moment. Redux. Okay. So in today's edition of shear and bending moment diagrams, we're going to add a little bit of realism here. So say I have my favorite cantilever beam, right? Say my favorite cantilever beam, I've always liked titanium. Here, where is it? There it is. 0.161. say that this beam is made out of titanium, which has a density of 0.161 pounds per cubic inch. Okay. Yeah, I don't need anything more than that. Cool. All right. Now, we've been saying that we could do a 3D problem, but we have to solve a cubic equation in order to get more circle flow from it. So we're only going to consider plane stress, and as such means we're going to treat this as a 2D here problem, and say there aren't any out of plane loads. It's all in plane. So the question is, what forces are acting on this?
Distributed load.
From what?
The weight.
Right. Is that distributed load uniform?
Yes.
Why?
Because it's uniformly dense.
Yeah. It's called, this is a uniformly dense beam, because it wouldn't make sense if it wasn't. So the weight is going to act as a uniformly distributed load. If I throw some dimensions at this, let's call this a 1 inch tall by 3 foot long, and say its depth or which call thickness is 1 inch. That's like the in to the board dimension. Let's call that. Now, if I wanted to, now it's called the weight is a uniform load pressing down, but because it's a 2D problem, let's try to get a better feel for that. Instead of having a volumetric density, so something that's a weight or a mass normalized by volume, let's try to populate that into a linear density. So like a density per foot of the beam, because that would make more sense for a 2D analysis, especially if we're doing a shear and bending moment diagram. So how do I get that from here? Actually, let's make this like. Say again? This?
Yeah.
Okay. So if I multiplied this by length, I'd get like a pounds per inch squared, right? Okay, so now it's like a force per an area. Okay, so let's walk through this a little bit more. So in a sense, I want to find out, how do I want to say this? I want to find out from this density how much a cross section of this beam will weigh. So if I wanted to find out how much this entire beam would weigh, what would I do to this number? If I want to find out how much the entire beam would weigh. Right, so I multiplied by length, width, and depth, right? If I want to find out how much a cross section weighs, is what would I do? If in order to find the whole beam, I multiplied by volume. If I want to find how much a cross section weighs, I multiply by what? The cross section would be like, which would be like an area, right? So move this number up, t equals ½ inch. So if I wanted to find like a linear density, I'm going to call it lambda for now, so I have a different number. It'd be like rho A, and that gives me units of pounds per inch. And so a weight per length Okay, you all follow? Cool. And what area is like a 1/2 inch square? So this should end up being something like what? 0.085?
0.0805.
Yes. Pounds per inch. So that's the linear density of this beam. That's how much 1 inch of length of this beam weighs. 0.0805 pounds. All right? So that, let's say that is W, our distributed load. All right? Just going to erase this for a little bit more room. So that turns, it's called, so that turns into our distributed load there. Okay. Cool. All right, so now we have our load, we have our beam. Are there any other forces poking at this? Forces or moments?
Air resistance.
Why do we pick the area for the cross section at the top? Okay. So we picked the area, of a transverse cross section here because our shear and bending moment diagram goes out along the beam, right? Like we care about the loads at particular sections longitudinally, at least based on the loading. If we had like a load that was distributed this way, we'd probably care about it in the other direction, right? So, but because we care about loads on sections going like that, it would be advantageous for us to find the weight for a particular chunk of the beam going out along the length, right? Because if I draw a cross section, if I take a cross section, I go out like that, and I have shear force and bending moment. I need to know all the loads acting on this particular section, right? So if I have some load distribution that's characterized by pounds per length, force per length, and I know what this length is, I can find a load, right? So that's why we care about it in the long direction. All right, cool. All right. So, what other forces and moments are acting on this thing, if any? Air resistance is a no.
Some reaction force from the wall or whatever.
Yeah. So, call it some reaction force. Anything else? Why? Why would there be a bending moment? Also fair. But 0 at which end? This end? Yeah, bending will be 0 at both ends. Well, actually, no, it won't be 0 at this end. It'll be 0 at this end. It won't be 0 here only because it's fixed at this end. So these hashed lines means that it's fixed to the wall. It can't move. So there has to be some concentrated moment there too. Okay? And if we throw some positive directions on this sucker, we can do statics and figure out what those two things are. Like if we did summation of forces in the y direction, have like what FR minus our distributed load. How to get a force from that load? Right. It's called, it kind of just like finishes up the density, he thought. This is a weight per length. So if I multiply by the length of the beam, I get a weight here to the beam. So equals 0. And FR equals?
The vertical component?
Yes. 0.2415 pounds?
0.2898?
Okay. I was guessing. Yes. Oh, yeah, because it's not times 3, it's times 36. So 36 times that is 0.2898? Really?
Wait, 36 times the food.
That sounds better.
That's not
I thought there was an extra point in there.
0.898?
Okay.
You came first.
Okay, so you do that, you get the reaction force. Sweet. Now if we do the same thing for for the reaction moment. So this is summing moments at the wall. Call it point A. Now we get MR. It's the reaction moment. Then we have this big distributed load thing. How do I get a moment out of that crap?
You do the x-axis is half the length.
Right. Because it's uniformly distributed, I can assume that it's acting at a point halfway along its length. Yeah, halfway along the length of the distribution. That is, if the distribution only went out to like there, I'd have to find the halfway point for that now, and so on and so forth. But it doesn't. So hey, it makes our life easier. So MR, is this a positive or a negative moment from the distributed load? Negative. Yep. So play our games with force times what you call a moment arm, and all that equals 0. So MR equals
52.164 pound inches.
52.164 pound-inches. Okay. Cool. All right. Now let's rock and roll. I'll say here. I'll probably put it on in the practice later on. But a fun fact: if you have some load distribution that's which I'll say triangular. So it's defined. So like W would be like some load times X location plus some intercept with some triangular load distribution like that. Kind of where you're measuring from. I'm going to say this. It's called this, which called the centroid of a triangle is always 1/3 its length from the the tallest part of the triangle. Fun fact. So if you wanted to find, so it's called kind of the centroid of this, the middle of this is just where you assume it to be acting. Which called for a triangularly distributed load, you can assume that it will act at 1/3 its length from what's called the tall side of the triangle. Fun geometry point of the day. But also because triangular load distributions are handy if you're trying to approximate stuff. Like say a cantilever beam that's being anviled, that's hanging off the edge of a thing, and you want to try to compute the loads in this portion that's sitting on top of the support, or say you have a wing creating lift or whatever. Be a handy approximation. Anyhow, that won't be the last time that you see it. All right, so you get that. So if I want to make a shear and bending moment diagram, what's the next step?
You almost have like a shear diagram on the top there.
You almost do, but you don't. So how do we bridge that gap?
Put some units on the left side.
Put some units on the left side. Okay, how about we draw a new free body diagram? No, no, you can't, because it's distributed always and everywhere. Yeah. You can only consider it to be acting as one force when you're doing in a particular location, when you're doing statics on the whole structure. But because from a materials point of view, we care about the internal reactions all along the beam. We're now very sensitive to how loads are distributed. It's kind of like if you're laying flat on top of a pond of ice as opposed to like standing on a pond of ice. Like it matters how the stresses depend on how the load is distributed. So we can't ignore that fact here, or we can't simplify it out, put it that way. Okay, cool. All right, so there's shear, and actually we're going to think that way. I think it'll give us a better result. Okay, there's our FR, MR. We have some load. We'll go it out in X. Okay, so that'd be like our free body diagram for an arbitrary section along the length. There, you might say that the load is continuous along the length. So as opposed to like previously, we had to make a new free body diagram every time that we crossed a new load, right? Here, even though like you always have a new load, it's a continuous load. Like we can make an expression for how the weight, for how this force pressing down varies with X, right? Because this is a linear density. So whatever our X is, multiply that by W, I have of the force that's pressing down. Make sense? Cool. So because it's continuous, we don't need to worry about making a new diagram for anything. This is our one free body diagram that does the entire beam in one shot. However, we are going to come up with, because it's continuous, it's not piecewise. Piecewise meaning that the equations only apply in certain intervals. This is what's called continuous. It's applicable for the entire beam. Because it's continuous, it means that we're going to have a shear and bending moment diagram that look much different than before. So let's figure out what that looks like. I need to get more space. So erase. I heard that. Again, I believe that's the definition of redux, I think. Yeah. Yeah, you go through it again. Yeah. Thank you. No, that's what's like for, like we had shear stress redux and bending moment redux, and yeah. I was just trying to be linguistically fun. Oh well. R. This was going that way. MR. That's W equals 0.0805. 805 pounds per inch. Okay. Thickness was a 1/2 inch. Height was 1 inch. If you need any of that. Total length was 36 inches. There's an X direction. Squirrel away some positive directions over here. All right, we should have everything that we need. So that's if that's my FBED, if I have my beam, X is going out that way. There's F shear, there's bending moment, there's distributed load, there's some reactions at the other side. What's my first step? What do I do?
Find what F shear is equal to at X.
Okay, so it's like a sum of forces. And for starting with F shear, it's like a negative F shear, right? We have positive FR, and what's my last term? Does that have the correct units? Times X, right. Okay, so if I work out the math here, Fs equals like a negative Wx plus Fr. Oh, come back here, smartboard. Calm yourself down. Cool. And that looks an awful lot like a linear equation, right? Like y equals mx plus b. So if I plotted this. Right. So the slope of this is W. We're starting at FR. So starting at 2.898 pounds, whatever is going on here. Yeah, 2.898 pounds, and slope down to 0 shear stress at the end of the beam. Because if I multiply W by 36 inches, I should get that number again, right? Cool. So that's what our shear diagram looks like. It looks like now. All right. So now what does our bending moment diagram look like? Woo! Yay! Integrals. And because I have that going the opposite direction, our sign should even work. Should even work out. But let's be sure and do the actually work out an expression for it. So if I'm summing moments at that section, which I've arbitrarily called point B, I have some bending moment some internal bending moment going in the negative direction. I have some reaction moment at the wall. And then I have some moment being caused by the load distribution, by the weight. And what's that? W. Does that have the correct units? Times what? Okay, so there's a lot of stuff going on here. Okay, so if I go by X over 2, my units are what? No, just pounds, right? The units here are pounds. This is units. The first guy are pound inches. Units the next guy are inches. Becomes pounds. I'm still missing out on something. If I multiply by area, I do get to the correct units, but it's not the right physical quantity, right? So what do I have to get first? Right, I have to get a force times a moment arm. So what's the force acting on this length of the beam? Yeah, Yeah, same as in which call our shear equation. The force is just Wx. Now what's the moment arm?
X/2.
Right. And that's our bend, and that's our bending moment. Which, if you look ahead,
The FR, FR, because I guess the best one.
oh, you are correct. Thank thank you. Sorry, I missed one. FR makes the bending moment around this is too, right? It makes a moment around this too, right? Because it's a force acting at a distance. So we have to account for that guy. Force in the negative. It's a moment in the negative direction, so like FRX. And that's all the bending moments going on here. And if you work out the algebra, you get this really wild solution that is a quadratic. It's like before, bending moment was always linear because the shear loads were always piecewise constant. Now that the shear loads become a linear equation, it means that bending moment is now quadratic, second order. If we had a triangular load distribution, that would mean that bending moment would actually become cubic because the shear loading would be which would be a higher order too. Or sorry, no, actually no, it would still be a quadratic because shear loading would still be linear. Sorry. And anyhow, so that's what we get. If we wanted to graph that, could say, okay, at x equals 0, we'll start off at MR. And then it's, how do I want to say this? For small, that should dominate first, right? Yeah, I think it should go something like that to L. Right? Yeah. And that's a quadratic, I promise. Actually, let me just redraw that so that it looks better. Something like that. Because it's opening up. So it'll decrease quadratically to the end of the beam where it should equal 0. All right. We happy with this? Excellent. I am glad that I have fulfilled your mechanics and material experiences with the best mechanics and materials class you will have this entire day. All right. That's pretty much all I got for today. I'll try to have a practice problem up with this in the next couple of days. If you have any questions to bring to recitation tomorrow, please do so. Else I'll make something up. Thanks for starting.
So practice problems you're sending out, are they going to be close to what's on the final? They're still figuring it out.
Yeah, they'll be good practice for what's on the final because what they do is put a lot of stuff together.
Yeah.
Yeah. So, yeah, it might not be exactly what's there. The final might be a little bit easier, but they'll be good practice for it.